So welcome everyone to Carlos Abellán from Quside Technologies here in Barcelona. If I am correct, you study telecommunications, right, at UPC?
Correct.
And then later you did this European master in photonics. And after that, Carlos studied, did a PhD at ICFO in photonics as well, where he worked under the supervision of Valerio Pruneri and Morgan Mitchell to develop this quantum random number generator that we will learn about today. And yeah, you also participated in quite some exciting milestone experiments. For example, the first demonstration of a loophole-free Bell test, where your QRNG was, I guess, one of the key elements to realize. And further, he pushed the miniaturization of the technology via photonic integrated circuits. So yeah, let's welcome everyone, and the stage is yours, Carlos. We're happy to have you here and learn about everything.
Thank you very much for the introduction, Fabian. Please let me know when you can see the slides.
Yes, yeah, we can see it now, and everything seems to be fine.
Very good. Well, thanks a lot for having me here. I'm very happy of participating and joining this community, and let's hope we can sometime soon meet in person here in Barcelona.
Yeah, that's actually the initial idea, to have like real meetups and talks and I don't know, whatever. Let's see.
So, I'm going to be jumping into the presentation. I'm going to be talking to you today about random number generation. This is a topic I've been working for several years, and now at Quside we're working on it. So I hope I can share some knowledge and information with you. I'll start with a video, and I'll continue afterwards.
We live in a data-driven world, surrounded by devices that make our lives easier. Electronic chips and communication networks enable today's commodities, where a massive amount of data is continuously shared amongst us all. However, we have reached a time when our ability to protect and digest this information is hitting unexplored limits. At Quside, we believe quantum technologies will help us overcome these limits. Our mission is to help build a connected world with safer connectivity and more powerful computation. Quantum technologies offer the chance to discover, create, and deploy innovation consistently in a way that will transform industries and our daily lives.
So I hope this provides some context. I wanted to start discussing a little bit where all of this started, just to give some background. So all this initiative was initiated at ICFO, the Institute of Photonic Sciences, which is located here in the area in Castelldefels, around 2008. So at that time, in the groups of Valerio Pruneri and other people here at ICFO, there was a project for building a quantum transceiver for doing quantum key distribution with space. And at that time is when me and some of my colleagues today joined the initiative. We joined in this project, but then we started working on a new technology that was based on producing random numbers for applications in security and computation. And some of the things that we achieved over that period of time between 2012, 2017, more or less, was we demonstrated the technology to work at a very high rate. In particular, 40 gigabits per second were demonstrated in the lab. We also developed new methodologies for testing randomness, which is something that is a kind of fascinating field. So randomness and how to test it and what is random. So we developed some methodology. And this combination, the performance of our technology plus the ability of diagnosing how good the randomness was, led us to build a series of prototypes of technologies that were used in something that Fabian was discussing before, which were called the Loophole-free Bell test in 2015, which were really landmark results in physics. So some very cool experiments that used our technology, and we were very happy of being able to help there. And the last thing that we achieved at the research level was we managed to integrate all of this photonic technology, all of this photonic quantum technology on a single chip. Actually, we did different experiments with different materials, silicon photonics and indium phosphide, to be more precise. And we managed to demonstrate the full integration of this. And really, this was a time in which we decided that we did the homework in sense of the science, and we wanted to take this a step further and build a company. And that's Quside. So Quside is the result of all of this research and years of R&D effort, consolidated into a startup initiative that aims at bringing QRNG technology further, as well as other technologies down the road. So we are, again, spin-off from ICFO. We're located in the Barcelona area, and we have this track record in quantum and photonics technology. The vision and the mission of our company is very simple. We believe that quantum technologies are going to be helping in addressing two of the biggest challenges that we're facing. One is in protecting information better and for the long run. And the second one is on building more powerful computation capabilities. Not necessarily quantum computing, but going there in that direction. This is a bit the summary of the paradigm that is really behind the work that we do. So as time goes by, we continue to increase computing power, right? Research is going to go there, technology is going to go there, innovation is going to go there. And as we increase computing power, there are more things that we can do with data, new applications, new services, new technologies, artificial intelligence, self-driving cars, you name it, right? So more computing power today means new business models, new technologies, more convenience for consumers. The challenge is that at the same time, more computing power means more risks to data security and data privacy. So there is a point in which if we have enough computing power, the way that we do security today, which is called computational security, it's a paradigm, is going to drop. And then at that point, we will not be able to protect information. And then at that time, we will have a lot of computing power, but it's going to be useless because we will not be able to use it for practical application. So the sense is that the utility that we can get out of this computing power is going to drop together with the ability to protect information. So really what should happen, and there's many people working on it, including us, is in making sure that security doesn't drop with increased computing power. And that means changing the paradigm behind data security today. So bringing this quantum safe security paradigm to any industry. And then as we achieve that, we're going to be achieving that utility is going to grow together with computing power. So those are the two things that motivate us: safer connectivity and more powerful computation. So this is what's behind the efforts that we do. What are the options that are on the table and that you probably read about or you can read about? So there's mostly what people call post-quantum cryptography. And this is a field that basically is looking at exploring new types of algorithms for doing encryption, which are not vulnerable by quantum computers. So it's the same paradigm security-wise, so still computational security, but the idea is to find new algorithms that are robust against quantum computers and other attacks. The second paradigm is quantum cryptography. And here we can find at least a couple of technologies. One is quantum random number generation. The other one is quantum key distribution, which is another part of the security chain. This is not based on computational assumptions in general, but on physical assumptions. And this brings new recipes, new set of a new toolkit for solving the security problem, which is what everyone wants to achieve. Some news, and just as an illustration that this is a field that is evolving very fast, all of this is over the last 30 days, right? So over the last 30 days, a group in China led by Zhang Weipan has published a new incredible result on a massive QKD deployment in China that includes up to 700 links in the ground and lots of kilometers of space connection. So this is an impressive result. And on the right, there is a similar news that says that there is a European consortia that's going to be working on quantum communications for space, right? So this is something that both in China and Europe and in the US, there are efforts in this direction because it's really essential for the protection of infrastructure at any level. And below, we can find a couple news. One is that Munich is going to be investing a lot of money in what they call the Munich Quantum Valley, which is very exciting. And let's see what will come out of that. Definitely good news for the German ecosystem. And on the right, here in the bottom right, there's a new report. I encourage you to have a look on quantum random number generators, both on what they are and what they're going to be used for and what the impact that they can get. So this is a pretty interesting read. It's really a couple days old. What are some of the key factors that are leading people to change and migrate? So one of those is that really people know that security is at risk, but sometimes that's not enough. The good news is that there are standardization bodies like National Institute of Standards and Technologies is going to be putting out new standards for security, aligned to some of the things that back in 2016, the NSA already said, which is, hey guys, we should start looking at transitioning into quantum resistant algorithms. So really, this is going to be enforced at the standardization level, and there's going to be a need to migrate into new crypto. And here's a question that a lot of people, or that we hear quite often, right? So the thing is, okay, I buy it. We have a security problem, or better, we will have a security problem when we have a quantum computer, but we don't have a quantum computer yet. So why bother? So we don't have a problem. So that's a fair argument, but in some axes that's incomplete because of at least 4 reasons, right? On the left, there is something called, or the people call store now, decrypt later. Basically, that means that something you can do today and that some people are doing today is harvesting encrypted data. So basically, you just store communications that are encrypted with today's cryptography with the promise that, let's say, in 10 years or 15 years, you will be able to break that encryption. And when you're talking about national security data or health records or financial records, that's a problem. Really, you need to keep data longer than that, or you might have an issue, as well as for some private information and privacy of individuals and corporations. So that's a problem. So the sooner that we can migrate the cryptography that we use, the sooner that we will get rid of this store now, decrypt later. So we're going to be seeing a lot of traction in high-end systems like governmental, military, data centers, financial, health, that are going to be driven by this. The second thing is that it's going to take a long time to migrate to a quantum safe infrastructure. And some people say that more than 15 years. So really, in 15 years' time, we should definitely be ready for tackling this security issue. So the sooner you start, the better. The third one is for set of products that are going to be really in the market for a long time. And you can think about the automotive industry, right? So you're going to be designing a new car that you're going to bring into production in, I don't know, 2, 3, or 4 years. And then someone is going to buy that car and is going to be driving it for 10 years. So you're talking about a lifespan for that product of 15 years. And in the automotive industry, data is going to be increasing in value, right? So self-driving cars, automation, digital experiences. So making sure that data is protected is quintessential for that industry. And proactivity is emerging to bring in quantum safe technologies. And the last one, as I said, is regulations and standards. So this is something that is also driving the change. 2 of the key ideas here that you will hear about is using quantum technology, so this quantum enhancement of the security portfolio, and the crypto agility piece, which basically means that you and your organization and your infrastructure can migrate new algorithms as soon as they are available. Really, that's sometimes not the case. So there's some people that to migrate a new protocol in an infrastructure, they could take a long time. So designing in a crypto agile way is something strongly recommended today by some of the providers. Before I dive into the QRNG part, last piece of the context is for those of you that are not in the field of security, there are 3 things that we need to protect information and protect the message, or to build a secure communication channel. The first one is what we would call a hiding mechanism, right? So we have a message and I want to send it to Fabian. And then what I do is apply one of these hiding mechanisms. It can be, for instance, the algorithm AES, right? So then what I do, I take my data, I scramble it in a given way, and then what Fabian does, takes and scrambles the data, so applies the reverse operation and reads the message. But because we all know this is standard, we all know to apply it and reverse it, this is really not enough, right? So you need the second ingredient, which is generating an unpredictable secret. So what I will do is I will take my message, I will take a stream of random numbers that I am the only one to know, and I'll combine those two things with a hiding mechanism and put it on the cloud so that Fabian can then read that message whenever he wants. What I'm doing with that is that this is called key generation. If someone gets that package at some point, they will not be able to decrypt it because they're missing the secret. They don't have the secret, which brings the third ingredient. We need to distribute secrets, because if I want Fabian to have it, I need to send him these random numbers. And this is the key exchange, right? So we have the algorithm, the key generation, and the key exchange pieces that are essential. And what we're talking, when we're talking about quantum enhancement or quantum safe security, we're talking about using algorithms or technologies for the algorithm or the distribution that are safe against quantum computers, and quantum random number generation for generating the unpredictable secrets. So this brings me to the first, to closing the first part, and then I'll jump into the what do we really need to do to generate unpredictable secrets. And the point is, an unpredictable secret in the sense of cryptography is generated by a random number generator. This is what you do. This is what a secret is in this context. So another question is, how do we generate random numbers? So this is something that people used to do back in the old days. So this is a book. I actually have this one at home with a few random numbers. You can open the pages and there are random numbers in there. And I really encourage you to go to Amazon and find for this book and read the comments, right? They are very funny. This is one of those. This is a folk that says, I bought 2 copies of this book, and the first copy perfectly predicts what the numbers in the second copy are going to be. I feel cheated. So, and you can find many of those comments. It's funny, but it reflects something which is very important. A random number per se, you can copy it, right? You can take a copy of this book and predict it. So there's really no unpredictability in it and in there. So what is important when we're talking about random number generators is really about the mechanism to produce the random numbers, more than the random number per se. The random number, once generated, can be copied. But the generation process is what makes it truly unique. So one of the ways for generating random numbers when the computers were invented, this is the picture of the ENIAC computer, back at the beginning of last century, there were a few folks like John von Neumann and Stanislaw Ulam that invented what is called today the Monte Carlo method that uses random numbers. But they didn't have random number generators at that time, so they invented pseudo-randomness. That's an algorithm that produces a sequence that looks random in some sense, statistically speaking. And that's one of the first, let's say, random number generation techniques of the IT connected to computers. The problem with pseudo-randomness is that actually it's just an algorithm, right? So it's something that looks random, but is not unpredictable. Actually, it's the other way around. It's fully predictable. So in the context of security, that's not what people use. Well, what should be used, right? Some people might do it, but then you have a system that is not secure. So how do we do it then? If we cannot use pseudo-randomness and we cannot use the book, so basically the concept that is really important here is entropy or entropy sources. This is a physical system that fluctuates in a random way and that we are able to sample it, measure it, and then we measure it, and this is the core ingredient of a random number generator. And there are different types of entropy sources. There are entropy sources, for instance, some of the first mechanisms was taking where the position of the mouse of a user was on the screen and then collecting that. That was some sort of entropy that people could collect. That was really not enough when systems scaled, when we built the internet and so on and so forth. So people started building chipsets that were based on some classical fluctuation or process and then measuring unpredictability from there. Or today, technology is maturing and we can use quantum processes, which is inherently the only way to generate actually unpredictable information. Classical physics is predictable, quantum physics is unpredictable. So this is actually the best way to do it. What is the challenge? Generating random numbers is hard. It's hard, but it is really fundamental in security and computation. And one of the reasons that because this is hard is that because this is not a problem that software can solve. You really need to get your hands dirty and build hardware. You really need to get it from the physical world. And as I said, one of the best places to go and measure these entropies in quantum physics. So you really need to find a quantum process that you can conveniently sample and get entropy out. At the practical level, if you generate poor random numbers or you do not deliver them well, so you can have the best random number generator from the most random process in the world, but if you cut the wire that connects it to the processor, really it's of no use. This sounds silly, but this is something that happens in practice. So really the full chain of generation and delivery is something that should be taken care of. And the last, if you've studied telecom or cryptography, there is a rule of thumb that it says, don't base your security on obscurity. So basically, not because you're making a system that is very complex, you're going to have more security. Actually, it's the other way around. Everything in a cryptographic system, even the code of the algorithms, is public. And the only thing that should be unpredictable and the only thing that produces security is the randomness that you use, the entropy that you use. So we use this sentence, don't base your randomness security on obscurity, in the sense that it's very important that these entropy sources are transparent, that users, that customers know where they're getting the entropy from, and that they can verify that this physical process is working well. And I'll connect with this in a minute. How do we build a QRNG? Or RNG in general? You need these three ingredients at least. The central ingredient is this entropy source, right? This thing around here. This is what the physical process that produces the unpredictability. Produces a random analog signal that we digitize, and then we have a digital stream. These are ones and zeros. You have to do something. It's a post-processing step. It's called conditioning or randomness extraction. There are different names to it. But then at the output of this block, you get a random stream that you need to interface with the system. And at the left side, because this is a physical process, you need the mechanism to control it and drive it properly, and measuring the quality and being able to diagnose if it's working well or not. This is one of the, actually, I think it was the first QRNG that was ever published and reported, right? So this is I don't know if I don't have my mouse. Well, it doesn't matter. So you have a laser.
We can see it actually.
I don't know where I am.
Okay.
Okay. So you have a light source that is able to emit single photons, right? Imagine that you have this. Then what you put afterwards is what's called a beam splitter. This is an optical piece that what it does is with 50% probability, it lets the signal through, and with 50%, it sends the signal up. And then you place two single photon detectors. So you take these ingredients and you have a very pure random number generator. In practice, however, this technology, single photon detectors, single photon technologies, the imperfections in the hardware really makes this device slow, expensive, large, and not scalable. So people need to find approximations or different schemes or different physical processes to implement this. And this is what I'm going to be telling you in a minute. This is the Quside way to a quantum entropy production. So we call this technology the phase diffusion technology, and it's really simple. So you take a laser. This is a device that we've used in telecom for many years. And what we do is we drive it from below its threshold level to above its threshold level. And basically the effect of this is a stream of pulses, of optical pulses. These optical pulses contain a phase that, because of a quantum process that is called spontaneous emission, is random. And then we can measure this randomness using an interferometer. We split the signal, and then this basically splits in two halves, and then you recombine the signal, delaying the pulses. So basically you interfere one pulse with the previous one. And at the output, you get a signal that converts the random phased information from this spontaneous emission to amplitude information. And now this is very simple. You place a photodetector and then you're done. You have a random output that you can digitize and use for cryptography and computation. At Quside, we've already put a product in the market based on this technology. We call it the FMC 400. It's a 400 megabit per second device in its standard offering, and it offers what we call entropy bounds above 90%. What this entropy bound basically reflects is how much of the signal that we're measuring actually comes from the process that we trust, from this phase diffusion process that originates from a quantum mechanical event. So 90% of our signal, really taking into account all of the imperfections of the hardware and all of the predictabilities that this can introduce, is really from a quantum process that we trust. And really besides the phase diffusion technology and the quantum random number generation technology, there is a special thing about this one, which is this FMC interface. This is an electronic interface that is designed for high performance systems that are used for encryption and computation. And we're shipping these devices. This is the first commercial offering. Something that we're very excited about, as I said, is the integration. This is a picture of a chipset that we built a while ago and integrated it. And this is the next stage of integration and scaling. So the previous product is ideal for these high performance environments, scaling in volumes. And so scaling the volume, the capabilities of production app and the cost down is essential for accessing some other markets. And this is a journey we're also in. So the next question is, how do we know it's random, right? This is a question that we've always been intrigued by, and we try to provide a serious answer connected to the Loophole-free Bell test experiments that we were discussing before, right? This was something essential for those experiments. We really needed to know how random the random numbers were. The Loophole-free Bell test were 3 experiments done in 2015 in 3 laboratories. That happened at the same time, so it was an exciting year, actually, and busy one. One was in NIST in the US, the other one in Austria, the University of Vienna, and the other one in Delft in the Netherlands. And they were going after this result that proved, basically implemented the Bell test without the imperfections that other experiments had, and that implied an important result in the field of quantum physics. So we used our technology, our phase diffusion technology. We built different boxes. And again, the important thing was how random the random numbers were. When you ask this question in general, people say, well, run a battery of statistical tests, and you can find those online. So you put battery of statistical tests and you will find some entries. You download that piece of software, you load a stream of random numbers, and then you either pass the test or you do not pass the test. That's an interesting exercise, but now think about the book, right? You take the random numbers of the book, we run it through the software, and we pass the test because that sequence is random. Now we take the sequence again, we will pass the test again. Now we take the same sequence, we will pass the test again. So really that doesn't tell you anything about the system that generates the random numbers, which is what actually produces the unpredictability. So the mechanism to answer that question really goes into measuring the physics. We really need to go into the inner workings of the entropy source and monitor it, interrogate it, understand it, model it in a way that allows us to know how much of the signal that we measure is quantum and how much is not, or how much of the signal is trusted because it comes from a process that we rely on, and how much of that signal comes from electronic fluctuations, thermal fluctuations, vibrations, you name it, right? Those we do not trust. We don't know where they come from. It might be an attacker really introducing those fluctuations to trick us. We only rely on the ones that we understand well. And those were the results. Those were the boxes that were used in the Loophole-free Bell test. There are actually 6 of those deployed all over the world since 2015. What does randomness metrology means more in practice? So think about randomness or unpredictability in the vertical axis and steps that you need to do. So we start from a trusted physical process, phase diffusion in our case. When we measure it, we detect it, and then we're introducing imperfections on it that we do not rely. This reduces the unpredictability. When we do the next step, which is the digitization, there is again digitization noise. All of this corrupts, it's called, well, corrupts or influences the process that we trust, reducing or introducing predictability. You might think you're lost at this point, but fortunately, there is a mathematical scheme that is called randomness extraction that allows you to recover the unpredictability that you had at the beginning at the expense of compressing your random numbers. What that means is, imagine you start with 1 million random numbers, then you might get the same quality of the original process by doing this randomness extraction, but you only get out 800,000, right? So you have to compress 20% out of your data. How much compression you need to do? Mean entropy estimation, randomness metrology is the answer. So you actually, with metrology, you estimate how bad the different imperfections are, so you can retrieve them. So this is a very important step in the engineering of QRNGs. And this brings me to the last piece, which is applications. for these quantum random numbers, and I'll be happy to discuss more about this. I'll give you a few examples. So again, if you read this report that I mentioned at the beginning, really from a couple of days ago, you will find different use cases there, from lotteries, casinos, IT and infrastructure, QKD, experimental research, public services, or allocation of scarce resources. So imagine that you had you have a given number of vaccines and you need to vaccinate. That's the amount of people that you can vaccinate in your country. So how do you select that? So either you start with the older people and then you start going down, or if you had to do it at random, you really need a process that is random and cannot be corrupted, because otherwise that would be very unfair. So this is really an important use case in different domains like sport or in lotteries, in gaming, and in different scenarios. Really a fair mechanism to generate random numbers. More connected to security, there are different domains. I mentioned some of those. Connected cars is one of those. Data infrastructure, data centers, and networking equipment, so on and so forth. Then there are exciting applications that are more consumer-oriented, like mobile devices. And we've seen in 2020 a mobile device that has been marketed with a QRNG inside, which is an incredible milestone for everyone building QRNGs for many years. So this is good news for the field. And then we have other applications like high-performance computation. And this is an interesting field that we've been doing a lot of work recently, and that we hope we can bring some news out in 2021 on high-performance computation. Couple of examples of projects that you can check also for more information. So we are a member of 2 Europeanly funded projects of the Quantum Flagship. One is called QRNG, with a few partners like Bosch or ID Quantique, KU Leuven, Trento, Geneva, ICFO, so different partners. And the idea is in improving European capabilities for random number generation. And in particular, what Quside is building here is an extremely fast QRNG. We've achieved impressive bit rates and an incredible engineering that our team has put together for this. The second example is the project Civic. There are a lot of partners here, so I will not name them, but there is a combination of component makers, network integrators, and telcos. And the idea is for building a continuous variable QKD system. I will not get into the details. This might be the topic for another quantum meetup. But the idea is doing quantum key distribution, not with single photons, but with macroscopic signals. And there are several groups in Europe that are really leading. One of those is ICFO, actually. And what Quside is doing here is building the random number generators for a continuous variable QKD system that has some special features in terms of the generation. So it needs a very high bit rate of random numbers and in a very specific distribution format. And to wrap up, and I'll be happy to take any questions from here. So quantum technologies are ready in many different arenas, specifically random number generation. And this is allowing us to tackle our 2 big objectives. So going towards safer connectivity and going towards more powerful computation capabilities for our customers and partners. So thank you very much. And I don't know if I can read the chat, or Fabian, you should.
Yes, thank you very much, Carlos. We have a couple of questions. So Samurai Brito asks, could these chips be put inside of classical computers, and could they increase the accuracy of computational tasks like Monte Carlo simulation?
That's what we hope for, and that's what we're working for. Yes, so there are 2 main applications for this technology. Again, one is security, and in this case, in computation, there are different advantages of QRNGs. One is quality, and this is very important, of course. It can improve the reliability of some simulation, and the other one is performance. So when you have a CPU and you have to run a simulation, you really want to use the CPU for running the simulation. You don't want to throw away 20% or 30% or 40% of your CPU generating pseudo random numbers that on top of that are not very good. So by having this piece of chipset outside of the CPU or the GPU or the FPGA, you're really maximizing the use you can do of your computing resource. So this is a very practical advantage, but it's a very relevant one. And again, if you stay in touch, I'm confident that at the beginning of this year, we're going to be showing some results.
Okay, interesting. Yeah, nice. And there's another question. How could we measure the high performance computation just by changing the traditional random number generator by QRNGs?
This is a good one as well as a hard one, right? So randomness is something that that is hard to test. There are two, as I said just in the previous answer, there are two advantages of running these simulations. One is quality, and there are a series of problems which are very specific, but in which very small quality imperfections can lead to bad results. And that is a mechanism in which we're demonstrating the advantage in terms of quality in a way that can be precisely measured. This is one. The second one is the performance advantages. So you really are having more performance available to you, and this is an advantage at the practical level. And the third one, which is connected to the two, there are several high-performance computing users that we've talked to, that we've interacted to, and that we're collaborating with, that they are not, let's say it this way, so they prefer not to use pseudo randomness in their simulations, because they don't know the answer to their problem. They are relying on that randomized computation to get the output, but they don't have a way to then test it, right? So they prefer to use physical randomness for running their simulations when it comes to making the final call. So this is several angles to that question.
Cool, thanks, very interesting. Okay, do we have two more questions at least? So we have seen with artificial intelligence that many applications are possible, but only a few can be applied on real-world problems right now. Which other applications can have quantum technology right now? That's a more general question.
Yeah, this is probably a broader one. So if we were speaking about random number generation, I would say any application today. I think it's a matter of scaling and cost at this point in time, but the technology is mature. Then we have other technologies, maybe quantum computing or quantum sensing might be others, or quantum key distribution. So I would say quantum key distribution is also quite mature. There are devices that you can buy off the shelf for very specific environments. Let's say the relatively high price makes them very specific to very high-end environments, but those are deployed today and can be deployed, and the telecom sector is really looking into that. And this project, the CIVIC one, is looking into building QKD systems that really reduce the cost and make them more compatible in the telecom sector. So QKD, I would say, is quite mature, and there are also very exciting projects going on in space, right? So this is another area that is being applied. Quantum sensing, I'm not an expert, so I prefer to leave that one to someone else. But I also know some colleagues in different companies that are also maturing in terms of being able to sense with more precision using different sort of technologies like NB centers or quantum imaging, different techniques. Quantum computing is also not my field, but what I would say is what I'm expecting over the next few years is very specific processors that can tackle very specific problems with a competitive advantage. So this will not be universal quantum computing whatsoever, but this is going to be applications that can start already benefiting from quantum computing per se. That's on one side. And the other side is going to be this field of physics inspired or quantum related quantum-based simulations, and companies like Microsoft, Atos, Fujitsu are getting into this domain. And I'd say there's a lot of interesting opportunities there in the short term.
Thanks. Adrian asks, if photons interact with the environment and lose some of their quantum coherence, how do you deal with that for generating the random numbers?
So in our case, our random number generator is based on continuous variable, right? So we're not measuring a single photon, we're measuring a macroscopic signal. So concepts of decoherence do not apply in our chipsets. So because of this, we're using a macroscopic process. I would say that there are also some interesting results, I would say more at experimental level, but that can use quantum computers for generating random numbers. But I would say that the complexity is quite simple. So it's probably the lowest time computation you can do. So the coherence should be a process to deal with easily. And then the point, and this is very conceptual, any real hardware that you use is going to have imperfections. So in random number generation, you will always have to deal with this. What I mean by that is even if you have a process, you have a quantum state that you really are going to be projecting perfectly into two perfect bases. In theory, that's great. You project it and gives you 1/2 each. In practice, that's not going to be the case. Your measuring equipment is not going to be perfect. Your qubit can decohere or move tilt one side, till the other, and even change with time. So this process of mean entropy estimation, which the result is setting an entropy bound. So in the worst case, how bad that is for you is essential no matter what.
And you, with your device, you reach already 90%, right?
Right.
So that's already pretty good.
So 90% for a device that operates at 400 megabits per second at least. This is an important concept. So generating randomness is hard, generating it fast is harder. So 90% is really at that speed.
The output, yeah, the actual output of the random numbers.
Yeah.
I see. Carmen asks, is there any other kind of computation theoretically that could become a threat to cryptography in the future if invented?
Maybe. I would say there is a field that is also very active, is on how machine learning algorithms can also pose a risk into the algorithmic piece of cryptography, right? So what I mean by that is the protocols that we use today, like RSA, are based on, again, computational security, but there is no formal fundamental proof that that is unbreakable or that that is a hard problem, right? So we, or people believe, because many years of research of the best researchers in the world in the crypto domain haven't been able to break it. So let's say that's right, and we don't have someone in a garage being able to break it because he is a smarter person, right? But let's assume as humans we haven't been able to find the solution. Can an algorithm find a way to factor primes? I don't know. So it's a kind of scary argument. So I would say artificial intelligence is something to take a look at in the context of crypto, and there's a lot of people looking at that. And then the other possible computing technology might be photonic computing. So using light to run computations, which is a field also growing a lot recently, for instance, for applications in AI and other sort of computation. Maybe that is another area that worth looking at in the context of crypto.
Well, we're waiting for your announcements. Ricardo asks, how is your QRNG deployed in an IT infrastructure? So similar to hardware security models, or how does it work, the integration?
That we go inside of those devices. For instance, inside of a hardware security module.
Okay, thanks. There's a more technical question. When determining the min entropy, do you consider different sources of noise as uncorrelated, or also consider potential correlations among them? Is it possible to see these noise models that you use?
This is a very good one. So I recommend, so there is a paper that is in the public domain related to the random number generators that we built for the Loophole-free Bell test. It's called FRESH, something like FRESH quantum random number generation for Loophole-free Bell test, or look for something like this in Abellán. It was published in Physical Review Letters. And in there, that was something we looked at, right? So we were able to measure all the different noises in our system. And then the question was, right, but how do they combine, right? Because it might be that they are correlated, but we cannot see that correlation when we measure them in a simple way or in an independent way. Fortunately, the methodology allows for treating those noises in a, let's say, you can tune your paranoia about them, right? You can make them you can assume in your model that they're going to be fully correlated, and then you get a much stronger bound. Let's say the bound will say that you have much less randomness, or you can combine them like what could be normal, that they are uncorrelated, and that would be the standard way. So you can even treat them, all them as correlated, all of them as uncorrelated, or select some of those that you do not particularly trust and treat those as fully correlated and the other ones. So there's flexibility. We call this the paranoia level internally that you want to apply in your design.
Mm-hmm. Okay. Samurai also asks if you can trust the Samsung Galaxy A QRNG chip.
I don't know. I hope so.
Funny question, yeah. Ivan asks, what is the probability for the quantum extraction to generate the same output from distinct inputs?
So does that, let me confirm the question. So there is this algorithm that is called randomness extractor. You put raw data in, it gives you extracted data out. Is that the question, Ivan? Or?
Yeah, I don't understand. What he says, what is the probability for the quantum extraction to generate the same output for distinct inputs? Yes, he says yes. That's that you got the question right.
Okay, so basically this is a typical. There are different ways to do it. This is very well explored mathematical processes. So this is typically a hash function. So you take an input and then you put it through the algorithm and put it out. So there are collisions inherent in there. Typically, you work with security parameters that are very small. So I would say it's a negligible probability, but this can be calculated precisely when you know your mean entropy, when you set your mean entropy bound, and then the compression algorithm, the compression factor that you apply on the hashing function. So basically, those three parameters, the compression factor together with your mean entropy, are going to be telling you this information. But it's really epsilon.
Thanks. Okay, so we have two more questions, I think, and then we can wrap it up. One is quite interesting here. Diego asks if there's any project of building a QKD network like the one recently put forward by China in Europe. What is the current status?
This is a good one. Publicly, you can find a project that is called Open QKD. This is a European consortia with many partners, and you can find a lot of information there. So there are efforts going in that direction. And
it's based in Geneva, right?
Well, it's, let's say, probably there is a location in Geneva, but it's quite distributed. So there is a core in Spain, in Barcelona, and Madrid, in Paris as well, Geneva. I'm sure that in Erlangen there should be something. So it's really located in different perspectives. The idea is that what's going to be happening over the next few years is that different European countries, and also at the more aggregate level in a European framework, there are going to be deployments of QKD networks, hopefully as what we're seeing in China, but really here in Europe.
I have also heard that there's a project here for Barcelona, no? The city of Barcelona wants to set up a QKD link. Oops. Okay. Next question. After you lose randomness by detecting the photons and digitizing the signal, do you recover it by throwing away a percentage of the numbers, or how does this process work?
So it's not just throwing away some numbers, it's really applying a mathematical function on a given input. I'll give you an example. So imagine that, so one piece is doing a hashing function, and a hash function, you can think it as a matrix with a given depth and a given, so both in number of columns and number of rows. So let's say that you put a vector at the input, which is your raw data, and then you get 1,000 columns, and then you get only, you get put 1,000 columns, and then you just put 10 rows. So you're going to be compressing your space from 1,000 to 10. So you're going to have a massive compression, but you're going to be scrambling the data not in an obvious way, right? So that matrix is composed again of random numbers. So you're just mixing up your input vector and compressing it into something at the output, but it's not as obvious as just throwing every third bit.
Okay, and he's asked, how do you know which numbers to throw away and which ones to keep?
So again, you're not selecting which ones to keep or throw. You're combining them in let's say, in a smart way. And there are algorithms that are standardized. So if you really want to be complying with standards, you're going to be using one of these functions.
Okay, all right. I think we can wrap it up here. Thank you very much for this interesting talk. And yeah, we saw there were a lot of questions. People are interested in this field. I mean, it's quite exciting and affects us, yeah, daily with our devices, computers, smartphones. Yeah. So.
Thank you very much for having me here, and I'll be very happy to continue joining this community remotely, but hopefully at some point also
Yeah, sure. Let's hope we can meet up
Beautiful
this
spot
year.
of the city.
Yeah, and Carlos, when COVID allows it, we will invite you to have lunch.
Excellent. That's good.
Sounds great. All
Thank
right.
you.
So thanks everyone for joining in here today, and yeah, have a nice evening.
Bye-bye.
Bye.
Bye, thank
Ciao.
you.